Okay, here we are with a familiar picture.
Yes, yes. So I'm hoping it's familiar enough that I can just sort of proceed without recapping too much. Except, okay, so this picture here is actually going to be right. This is a familiar picture, but we're going to also do something unfamiliar with it. So we're going to do two things with this picture. One is the same one we did last week, and the other one is a different thing that's also relevant. So the thing that we did last week was we interpreted this picture as a part of the Galois correspondence for extension fields of the rational numbers. You know, so the rational numbers is at the bottom over here. So let's see. This is actually my template copy, so I don't want to mess it up. So I'm going to try and go to a second copy here, if I can find it. That's the second copy. Where's the third copy? Down there. Okay. Second copy is here. Okay. So I can move it over. How does this work? I'm sure it's bad at this. Okay. So this is the copy where we have. Why does it do that? Oh, maybe I have to pick a pen here. Okay. What color should I use here? Black, maybe. Where's black? Over here? Sorry. Wish I knew how to do this. All right. And that wasn't black.
Wait, I see red is lit up.
What?
Red is lit up, so somehow you
Oh, red. Okay, okay.
end up choosing reds.
Okay. Is that black? I'm having trouble.
Yeah, I think.
Why are there two blacks?
That's a great question. One's a fatter tip than the other? I don't know. Anyway, no, probably not.
Yeah, okay. That's way fatter. I don't like that. How do I get? Oh, in fact, I see three.
The other black looks
Okay,
like
yeah. Okay, okay. I guess I want this one then, maybe.
Ooh.
Okay. This gonna work? Right. I don't like bold. I want to underline for my thing. Okay. So yeah, so that's what this base field is here. It's the rationals. And this one over here is the rationals adjoin W, where W is equal to our favorite primitive cube root of unity. So this is the Eisenstein field over here. And yeah. And right, and one of our big themes has been that the Eisenstein field, although it's a quadratic field, it's actually a helper field in understanding cubic extensions, abelian cubic extensions. And so we're going to have some abelian cubic extensions here. And yeah, I wasn't quite organized enough to do the good version of this picture where the horizontal rows are actually in the increasing order. So, right, I mean, these are actually the cubic extensions of the rationals down here, which are three-dimensional. Unfortunately, it's beneath the row where we have the two-dimensional extension, but that's the way it goes. And this next higher row appears six-dimensional extensions of the rationals, which are three-dimensional extensions of the Eisenstein field. And then look, this is a nine-dimensional thing. This is an 18-dimensional thing. And we even have some purpose, as it turns out, for this nine-dimensional thing and this 18-dimensional thing. But that was all from last week. And whereas we now have another version of this same picture that's going to apply to a different base field, but it's going to work remarkably similarly. And it's going to, again, teach us about Z mod 3 torsors, or let's just call them at this point, let's call them abelian cubic extensions of our base field. But now our base field is going to be the the Gaussian field.
Mhm.
So that's, I guess we'll just call it I or something for our favorite primitive fourth root of 1, also known as I. And let's see, I'm supposed to fit this whole thing into the screen here, so I'm not doing it right. How does this work? Right, maybe I should have. Yeah, let me just try to erase that. All right. Just so I could try to fit things better into the screen. So where is it now? It's down here. Okay, I'm sure it's better at all of this. Okay, and then we can see that that this is the Gaussian field. And this thing above it that used to be the Eisenstein field is now the relative Eisenstein field. So it's just, the Eisenstein extension of the Gaussian field, which we can just write as like that. Or we could also think of it in other ways. You could also think of it, if you want to, and that's probably important at some point, to think of it as the relative Gaussian extension of the Eisenstein field.
Is it also a cyclotomic field?
It is. It's the 12th cyclotomic field in the sense that it's got all the 12 roots of unity, 12th primitive units of, it's generated by the 12th primitive roots of unity. Which kind of makes sense because the Gaussian is the 4th and the Eisenstein is the 6th. And I don't know, is 4 and 6, what's the least common multiple? I don't know, right?
Yeah, I mean, I think it's that. I think that's how you do it. Yeah. Yeah.
Maybe it's something like that. I just get confused because you could think of the Eisenstein field as the 3rd cyclotomic field, but you could also think of it as the 6th.
Right.
So I don't know what's the best conventions to use there, but it gets me confused sometimes. So yeah, so we're going to we're going to really try to learn from the fact that we have this same little fragment of a Galois correspondence that's appearing in over both of these bases. So let's try to shift back and forth between them. Here's that thing go. Damn. I'm trying to get back to the other one. Okay. Damn.
Why does it seem to move horizontally when you move vertical?
Well,
oh, maybe because you copied.
Yeah, I copied them in a very sloppy way. So
okay, you'll regret it. Okay, yeah,
right. Yeah, I already we got lots of things, but so let's try to. Well, okay, so let's see. So this thing over, let's see. So first of all, what are these? I mean, it looks like we have an 18 element Galois group, which is the Galois group of this top field over this bottom field. It's an 18 element abelian Galois group. And let's remind ourselves of what it is. So it's I just try to get it to fit in a reasonable way. 1, 2, 3. 1, 2, 3, 4, 5, 6. I'm doing that right. 1, 2, 3, 1, 2, 3, 4. Okay, so this is kind of a Chinese remainder theorem picture. So this is a modulo 3 squared. This is modulo 7. And the things that are relatively prime to 9 are generated by this primitive element 4. So it's like the powers of 2. No, primitive element 2. Why did I say that? Primitive element 2, so powers of 2. And right, so that's, that's the little general linear group of Z mod 9 right there. It's that 6 element. Now we also have a 6 element general linear group for Z mod 7, but it just so happens that for our purposes we don't really use that. We just use kind of like a 3 element quotient group of it, I guess. So it's like 1 and 6 is this subgroup, and then it has these cosets, which I guess are 3 and 4 and 2 and 5 or something like that. And so that's how these little, that's how you interpret this as a Galois correspondence. The red dots are telling you the subgroup of this 18 element Galois group. Right, it just so happens that the splitting patterns that we're interested in are relative to this modulus, which is, I guess, 9 times 7 is 63. So we can express all these congruence conditions modulo 63. Modulus is 63. So and by the way, so how do we get that magic number 63? Well, let's see. How did we get the magic number 63? So well, it has a lot to do with the fact that we're studying abelian cubic extensions. And so it's really helpful to get these little general linear groups of finite fields whose sizes are divisible by 3. And 7 is a great example of that, right? The multiplicative group is size 6, so that's divisible by 3. That's why I chose the prime 7. So I'm going to do something. Well, let's see. And on the other hand, 9 isn't a prime, but it has a lot to do with the prime 3, which is very important here. So there must be some good reasons for having the prime 3 involved as well. Yeah, and I could say more directly what those reasons are if I understood all of this better. But we're going to imitate what we half understand here, what I half understand here, in the Gaussian case, everything relative to the Gaussian case. So let me try to draw that. So we're going to have basically, an isomorphic 18 element abelian group. And then again, the sublattice of all the subgroups of this 18 element abelian group. And 1, 2, 3, 4, 5, 6, 1, 2, 3. By the way, this isn't the annoying picture that I have to draw. I have to draw a big, a big one at some point. So let's see, what does this one have? This again is going to have 3. Am I doing this right? 3 squared. Except yeah, this is going to generate an ideal, but not an ideal in the ordinary integers, but it's going to generate an ideal in the Gaussian integers. So that's going to, you have to think about that ideal, that principal ideal in the Gaussian integers, where the element, the principal thing, the element that's generating it, the generator for the principal ideal is 9. So that's like a big 9 by 9 square or something like that. And that's the annoying picture that I might have to actually draw, this big 9 by 9 picture. But fortunately, I've already got the graph paper here, so maybe we can get it to work. And yeah, and okay,
So at one point you drew a little chart like this black thing here, and you filled it in with primes with the
yes,
in the Chinese remaindery kind of, well, primes are the correct
Sure.
moduli in both directions. So you could do that in the Gaussian case too, I guess.
that's right. That's right. And, you know, so we're going to pretend, or perhaps it's even true, that we really understand that, so that we don't have to, you know, we don't have to do a lot of the detailed work of filling in this Chinese remainder stuff. We can just,
Yeah.
yeah. So, so we're going, yeah, okay. So I think this is going to work. So we need a prime which has, we need a Gaussian prime which has similar properties to the ordinary prime 7. In other words, its general linear group should be of order divisible by 3. And the Gaussian prime that I chose for that purpose is 2 plus 3i. And, you know, this is supposed to help us illustrate how the Artin correspondence or the Artin reciprocity theorem works for in its most general cases. I mean, we're you know, we're still doing examples, but these are more general examples than our previous examples. So we're making progress from my point of view in intuitive understanding of the Artin correspondence and the Artin reciprocity theorem. And so let's see, is it at all clear why the general linear group modulo 2 plus 3i, modulo the general linear group of, you know, the Gaussian integers modulo this Gaussian prime, why that general linear group is of size divisible by 3?
So let's see. So I don't know. So the length of that number.
Let's try to draw a little picture of this, I guess here. 2, what is 2 plus 3i is up there? Am I doing this right? It's like a little square there.
Yeah.
And the, you know, the 4 corners are really just, I guess there's some sort of little Pick's theorem thing going on here. The 4 corners are all the same 0 element of the quotient, right?
Mm-hmm.
And then there's these 12 crossings inside, 12 vertexes inside, which are the 12 elements of the 12 non-zero elements of the.
Oh, okay. Okay. Yeah. I was just thinking about how the area of that square is 13.
That's right. That's right.
So I was wondering what was going on.
That's right. So that's right.
Yeah,
13 is the size of the additive group.
Right. Yeah.
12 is the size of the multiplicative group.
Okay. Good.
Is
that the smallest one you could find, by the way?
It's the smallest one with some property, I guess the property of not being an ordinary prime or something like that.
Right. Yeah. Okay. Yeah.
Or at least it's the smallest one I found.
That's the property. Okay. Yeah. Okay. Fine. It
might
seems
be the smallest one.
Seems sort of big, but that is, if you went up to 12, you might have hoped that there would be like some 9s.
Yeah.
Anyway.
Yeah, I'm finding myself, you know, I'm trying to pick small examples, and I'm finding myself getting, you know, even the smallest examples are getting ridiculously big now as
Yeah.
Yeah, but it's still sort of fun for me, at least. So right, I guess you can sort of right. I think in this picture we can sort of even see this where this 3-element quotient group is. Well, so right, there's we need a 4-element subgroup, right? To be the kernel, to give us a 3-element quotient group of this 12-element general linear group. So the 4-element kernel is going to be like right in there. That's like, the four cardinal, right? The four invertible Gaussian integers, 1i, -1, and -I. Right, that's a little subgroup of the.
Okay.
I mean, that is the whole general linear group of the Gaussian integers, but it's also a subgroup of the.
Yeah.
Of the.
I was expecting to see something that looked like a subgroup of the additive group, but this is a subgroup of the multiplicative
A subgroup
group.
of the multiplicative group, and it's usually a little cross
Yeah,
surrounding the origins, surrounding the zero.
right.
But the cross has somehow been the bars of the cross are very scattered.
Yep.
And so how do we depict this? I guess we could say this is kind of 1i, -1, -I. I hope I'm doing this right. And then there's these two other cosets, which I won't even bother to list. It's just the two other cosets.
Uh-huh.
And
You're making me want to draw. If I could draw while you were talking, I would draw like blue and red dots filling 4 blue and 4 red, filling in the rest of that picture there to those other cosets. But if it's really
yeah,
you
okay,
could do
yeah,
it.
that's I like that suggestion. Well, can you do the calculation for me? Where are the red ones? Let's say. So what are we using? Black, red, and green, I guess. Okay, where should the red ones go?
Well, you can pick a
maybe-
red one anywhere.
Maybe just like in the middle.
Yeah, I think that's sort of how it goes. Yeah, and then the green ones will be the others. Uh-huh. Yeah. Anyway, sorry. There's something satisfying about seeing it. Uh-huh.
Yes, yes. And so
Interesting.
call this red, you call this green. Okay. I wonder what 6 colors we're going to use for the columns. So we're going to have, the Gaussian integers. Am I back to black now? The Gaussian integers. Sorry. that's the, well, I'm constantly switching back and forth between the field and the ring of algebraic integers inside of it. So apparently I just, I just called that the Gaussian integers, versus actually the Gaussian rationals.
Yeah.
Just get used to me making that kind of mistake. Or you're probably already used to it. So yeah, now, okay, yes, but in this case, I really should erase the Q, and I should, okay, so it's the Gaussian integers. I really should emphasize that this time. Okay, the Gaussian integers modulo 9. So this is the 81 element thing. So how do I draw the 81 element thing? So this isn't a prime ideal anymore, right? It's this square. Is that an accurate description? It's the square of a prime ideal. So
do you even need to do this?
say that again?
Do you even need to do this? Are you going to do something with these numbers?
I kind of like it. I find it instructive.
Okay, fine.
I
don't mind that. Once you get up to 81 things, I start getting
sure
a little tired out.
Oh, I didn't do that right, did I? 1, 2, 3, 4, 5, 6, 7, 8, 9. Why did I draw 12 instead of 9? All right, let's try to use the eraser somehow. It didn't quite work. Let's try that again. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, am I doing that right? Except, wait a minute. Let me think. I mean, somebody claimed to me, some Chinese person, at least they claimed to be Chinese. They claimed that the Chinese tend to use the vertexes like in Go, and the Westerners tend to use the squares like in chess or something like that. I mean, he claimed that this was throughout the cultures, but I'm not sure I believe that. But
If you had like prisoners, they could be playing Go and chess on the same board.
right.
Didn't have
I've always liked the fact that you can play two games of checkers on the same.
Oh, yeah.
Also.
Right.
Although one of the pairs of players has to be made out of antimatter because, you know, it's different orientation or something like that.
Oh.
So I think right. Okay. Maybe I can just, let's see. Why isn't this doing this the right way? Why isn't it giving me the, let's see. Block. Okay. Oh, I thought it was going to give me, okay. I have to use the eraser again. No, that's not right. I wish I understood how this works, but the eraser, okay, eraser. No, why isn't it doing that? Oh, because I didn't choose the eraser. Okay. Choose small eraser. Okay. Use it.
Seems to really want to mark out an area.
Why didn't it give me the eraser head here? Okay, yeah, maybe I had to. Okay, let me try it again. I don't know what it's doing. Let me try again. Okay, there it is. Sorry, I'm so incompetent. This. So am I doing this right now? Okay, now maybe I screwed up again. Maybe it really should be right. It should be. How does this work? I guess I have to decide whether I'm doing the Chinese way or the Western way. Well, all right, I've already been using the Western way, I guess. So sorry for all this going back and forth, but I guess I need a 9 by 9 after all. I was changing it to 8 by 8 because I was going to use the vertexes, but yeah, so it's really the 81 centers of these 81 squares. And right. So what is going on here? Why are we doing this now? So which right. Let's see. So let me go back to the previous one, the one over the ordinary integers here. So where is this? Yeah, so let's think about this Galois correspondence for the ordinary integers as the base. And let's think about this one right here. Let me circle it or something like that, or let me just notate it with a label of some kind. So what am I trying to say? This is going to be, right? This is going to be the ordinary integers with the cube root of the primitive cube root of unity. So this is, you know, I mean, we just think this is our favorite 9th root of unity. And you can tell that this is the right one here as compared to these ones next to it. Because it's the one with the vertical thing, the vertical subgroup. So that the congruence pattern only depends on the modulus 9. It doesn't depend on the modulus 7 at all. So we're going to have the analogous thing to that over the Gaussian integers. So, you know, everything relative to the Gaussian integers. So let's try and do that. So where is it? This one's down here. Let's see. No, okay, it's right here now. Okay. So this one here is going to be what? It's going to be. So by the way, so that ninth, that was the ninth root if you remember, that was the ninth cyclotomic field. But this one is going to be, what is it going to be? It's going to be the, again, is it the 18th or the 36th? I guess it's going to be the 36th. Is that right?
So 9 and 4, the GCD of 9 and sorry, the LCM of 9 and 4. Oh wait, we're not. Oh, this one here. Okay, sorry.
Yeah. This is when, you know, this is I is 1 to the 1/4, and now this thing 1 to the 1/9. See, and that's going to be what? That's going to be a 6th degree extension of the Gaussian field. Right? Because I mean, the relative Eisenstein extension, that was a quadratic extension of the Gaussian field.
Oh yeah.
So this is going to be a cubic extension of that. So it's going to be a 6th degree extension of the of the Gaussian field. So that means that we're expecting, if I understand correctly, that we're expecting that down here we're going to have some
Cubic.
yes, but we're going to have, let me see if I'm saying this right. I mean, over here we're going to have a 12 element, 12 elements. 12 elements in this thing over here. Because it's going to be, okay. How's it going to be 12? So, I mean, what did you say? You said something. I'm not.
I was saying that
yeah.
the field that's above and to the right of QI is a cubic extension of QI. That's all I was saying.
This one here.
Yeah.
Yes. That's right. Not necessarily an easily identifiable one.
Mm-hmm.
But it is. Yes, that's right.
Yeah.
That's right. And so what am I trying to say here? That so first of all, I'm claiming that GL1 of the Gaussian integers modulo 9 is size 72. Should I say, is it obvious, or should I say why that is?
No, it's not obvious. I mean, I know I could figure it out, but
Sure.
different.
I mean, it's 8 times 9. So I mean, there's this little short exact sequence that goes something like this, right? It's like GL1 Gaussian integers modulo 9, and that maps down to the Gaussian integers, the general linear group of the Gaussian integers, the multiplicative group of the Gaussian integers modulo 3. So this is, so that's size 8.
Yeah.
And the kernel is the additive group of the Gaussian integers modulo 3. I mean, I'm not sure how obvious it is. We've talked about that before, though. We've mentioned it, I think. It's the additive group of Z mod 3. And there are good reasons why it is. So maybe I don't have to belabor what any of the good reasons are if I can't remember any of them. But what were you going to say?
Oh, Is this like an example of something more general? It sounds like you told me about some other example of this type of thing, but I don't remember. So,
Yeah,
I mean, you're saying that middle guy is, well, sorry, maybe
when
you're
you, yeah,
not.
when you have a
Middle guy
prime power,
sorry?
it's when you have a, this happens whenever you have a prime power, when you have an ideal, you're modding up an ideal that's a prime power ideal.
Is
So
that middle group the affine group or whatever you call it? Is it the semi-direct product of the?
no, it's an abelian group.
Okay, sorry. So it's just sort of some other extension. Yeah.
Yes, I mean, it's
Yeah, sorry, I don't know why. Yeah.
there
It's the
are.
only one that I ever thought of.
It's well, we have talked about this before, and it's a very standard thing, and there should be better things I can say about it. But for the moment, we can just accept.
Well,
Yeah.
well, let's see.
So yeah, this is
As long as I believe
size
that the
nine,
middle
this is
guy
size
has
8.
size 72, then I believe the sizes of everything you said. Yeah. That
Well, but I
implies.
mean, right, clearly the additive group is size 9 and the multiplicative group is size 8.
Well, I know that, but what I don't know is why the additive group is that kernel there. That's
Yes, that's right. Why is there this short exact sequence? Well,
well, I know, I see that there's some epimorphism,
yes,
and so there's some kernel, and so then there's just two possible 9-element abelian groups it could be. So
yes, but I'm saying whenever you have a prime power ideal,
a prime power ideal, yeah.
then this basically happens, that you get the additive group of of something,
Okay.
and the multiplicative group of the quotient ring.
Okay. Okay, I was just trying to figure that out. That's
yeah, I mean, there are really good reasons for it. I'm just not feeling smart enough to say anything intelligent about it at the moment.
okay.
And so that means we're expecting, right? We're supposed to have this index 6 subgroup. So an index 6 subgroup in this 72 element group is going to be 12 elements. And let me see if I can write down what the 12 elements are. I think I have them written down here somewhere. Where are they? It's yeah, okay, here's what I think they are. I think it's like 1, 8, I, 3 plus I, 6 plus I, 1 plus 3I, 8 plus 3I, and 1 plus 6I, and 8 plus 6I, and 8I, and 3 plus 8I, and 6 plus 8I. Did that come up to be 12 elements? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I think that's the 12 element subgroup right there. And I'm hoping I can just quickly show you where it is in there. Again, this kind of concrete picture helps me understand, if I can find this little picture here. Right. I mean, I'm just trying to basically copy that down, but I think it's like that element and that element. So this is going to, right? If you think about this is going to be invariant under Gaussian conjugation, which means that, which ends up meaning actually that it's symmetric under this diagonal thing, because it's symmetric under the rotation, on the Gaussian, the 90-degree rotation, and it's also symmetric under Gaussian conjugation. So it's, it's got like I just have to put in 6 of them. That's right. And then the other 6 will be by reflection, so it's like. there.
That was 6 plus I there, did you just drew?
I think that's right, 6 plus I, that's right.
Okay, yeah,
And I already drew one of the ones that you get by reflection, so there, I'm gonna draw 7 before I start reflecting. Let's see, so where are they here? There's one over there, is that right? Yeah, I think so. And then there's, might move over there. Oh, except those are the ones that are just reflections. I don't really shouldn't be drawing those. So 1, 2, 3, 4. There must be 2 more. Where the hell are they?
well, like 8 plus 6I.
Oh. Or maybe it's 8 plus 3I and 8 plus 6I.
Yeah,
Okay, and now can we see how to reflect those? Just this one, if I could figure out where it is. So it's like a night move. So maybe it's that thing right there.
Mhm.
And right now, pretend that I chose 5 other colors. You know, just like we did with the
uh-huh,
rows, we're going to have the same thing with the columns, but it's basically just this 12 elements and the 12 element subgroup, and then these cosets of it, and like that. So that's what we're doing here now. Okay, so I just yeah,
sorry, I'm blanking, I'm just briefly remind me why it's a 12 element subgroup.
Okay. Okay, because yes, we can predict ahead of time that it's going to be a 12 element subgroup because it's supposed to be an index 6 subgroup of this 72 element general linear group.
Right.
And the reason we know the reason we know that it's this index 6 quotient Galois group is because we're imitating in the Gaussian case what we already did in the ordinary case.
Mm-hmm.
And yeah, but on the other hand, why is it this 12 element group? That's a good question. Why is it this 12 element group? And so there's an important lesson here for me. I mean, probably important for other people too, but I think I didn't quite realize this. And this is probably going to be really important in understand. Well, it's probably going to be really important in understanding the Artin reciprocity theorem and the Artin correspondence. But what am I trying to say here? Well, okay, so what is this supposed to be? This is supposed to be the Gaussian splitting pattern. So it's a Gaussian congruence pattern. And then you can see it looks like a Gaussian congruence pattern, right? It's like, so it's superimposed over a copy of the Gaussian integers or something like that, which is this graph paper. So it's a Gaussian congruence pattern, and it's the modulus of this Gaussian congruence pattern is 9. And as opposed to this other Gaussian congruence pattern, where the modulus was 2 plus 3i. So, right, we're going to be dealing with some sort of interaction between the congruence modulus 2 plus 3i and the congruence modulus 9. Just like when we were working over the ordinary integers, we combined the two moduluses 9 and 7 in a sort of Chinese remainder theorem way. So now we're doing it with these other two moduluses. So can I just think about that for a moment? So let's see. This thing for 9 has a 72 element multiplicative group. The thing for 2 plus 3i that has a 12 element multiplicative group. So I just multiply those two together, right, to get the size of the relevant subgroup. Except that that's overkill. We don't really need that because, right, we're just going to end up with this 18 thing. But I think I'm trying to remember what this is. Is it something like 12 times 9? No, 12 times 72 is maybe 864 or something like that. Like I said, these numbers get annoying, but so let's try to learn something here by comparing this Galois correspondent subgroup for the relative ninth cyclotomic field compared to the actual absolute ninth cyclotomic field. Okay, so that was over the ordinary integers, right? Whereas, you know, when I say relative now, I mean relative to the Gaussian integers. So right, I mean, we had this congruence pattern that was really just didn't involve the modulus 7 at all. It was really just modulo 9, and it was just the first column. So it's really just saying that the primes that split are the ones that are congruent to 1 modulo 9, and that's the ninth cyclotomic field. So right, that's the standard way it works. That's a very simple splitting pattern for cyclotomic fields. So the splitting pattern is T is congruent to 1 modulo 9. And now we're trying to understand why is the Gaussian analog of that what I'm claiming it is. So I'm claiming that the Gaussian analog of that is this thing down here. And why is that? And I halfway at this point, I understand it in a very empirical way, but it's going to be very important to understand in a conceptual way. And so in an empirical way, what it is that this subgroup is really saying that what we've really got is the I was going to say the determinant of P, but perhaps it's more standardly called the norm of P. I think. Don't trust me on any of this terminology, but I think it might be called the norm of P is congruent to 1 modulo 9. So it's really, you know what I'm saying? We're actually borrowing the same old splitting pattern, but in order to apply it to Gaussian integers, in order to apply it to Gaussian primes instead of ordinary primes, we have to take the norm of the Gaussian integers, norm of the Gaussian prime, in order to get an actual integer, not necessarily a Gaussian, not necessarily an ordinary prime. In fact, it generally won't be a Gaussian prime. It'll probably be a
normal prime.
Normal?
Sorry, it won't normal. Sorry, you changed from say that over again.
I said
Sorry.
normal prime. I should not have said normal prime.
Well,
The norm of a prime is what I'm saying.
oh, okay.
The so this is this. Those are the same thing. That's how I got this 12-element subgroup. So in fact, right, and in fact, I did this by hand because it was ridiculous, but it was also surprisingly easy because all I had to do was, you know, put the norm of these Gaussian integers. So that's just right. That's just the radius squared of the Gaussian integer. So those are just, you know, sums of squares. And then, so I have those numbers, and then I just have to cast out nines, you know, old-fashioned elementary school arithmetic, to find the ones that are congruent to 1 modulo 9. And that's what these are. These are the Gaussian numbers, modulo 9, that are whose norms are congruent to 1 modulo 9. So that's evidently some general fact about how relative splitting patterns work. That you're really just copying the original splitting pattern, except that you're applying it to primes that live over an extension field. So to get it to be meaningful, you have to take the norm of the prime in the extension field. The prime in the higher base.
if you've got if you've got some algebraic number field that's not the rationals,
Yes,
then you have some extension of it. Is there some
Yes.
kind of norm of a guy in the extension that's equal
Yes.
to the guy in the number field? So there's like a
Yes.
relative norm kind of thing?
Yes, yes. And I think that's just called norm, I think. But
Okay.
again, don't trust me on any of this terminology, but that's what I'm trying to do here. And
Well,
what,
here you're taking a norm, you're going down to the, I mean,
but I
your
think
norms
that's,
are
I think that's some funny coincidence. I mean, it's really the norm squared, right? I mean, it's the, or I guess some people call it the norm. I don't know.
well, yeah, no, I'm sticking, I mean, I do mean the algebraist concept of norm, which is like. the
Well, let me
norm
say what
compared to
is the
the
algebraic
analog.
concept of norm here? What were you going to say? Yeah, go ahead.
I'm just gonna ask the same question again and hope you answer it the same way so that I feel that I communicated correctly. So
Yeah,
if you've got an extension field of an algebraic number field,
yes,
is there some kind of norm that you can take
yes.
a guy in the extension that takes values in the algebraic number field?
My understanding is yes.
Okay.
Certainly,
I used to know.
certainly for these abelian extensions, certainly for these abelian
Uh-huh.
extensions, but I think
Uh-huh.
it doesn't depend on the abelianness.
Uh-huh.
And we can say very straightforwardly, I think, what the norm is. And
Oh, I think it's something like you take the
yes,
product of all the Galois conjugates.
exactly. That's right. That's what this is. That's right. That's that's
that
right.
would-
That's what I was going to say. That's
Okay,
right.
sorry, but well, anyway.
That's right. That's
Yeah,
good.
okay, so that does.
Right.
But
And
in this
it's a
case,
good thing to
anyway,
do here. Yeah.
but in this case, when you wrote norm there,
Yeah.
that's the norm of a
Gaussian.
Gaussian prime. Yeah, okay, so the norm is a integer, plain old integer.
That's right. And right. And not necessarily a prime. I mean, usually not a prime, usually or often not a prime. It will be a prime power. It will be a square in this case. But more generally, I think it will be a prime power unless I'm screwing up. Yeah, I think it will. And
Sorry, here's a really dumb question.
yes,
Sorry, this anyway, it's embarrassing, but I've got to ask
Yes.
it. So is the Gaussian integers mod 9, is that a field?
no, that's why we
Okay.
didn't just take 81 minus 1 is 80.
Yeah, okay, duh, yeah, okay. So yeah. So mod 3 would have been a field, and then this is like the.
Right. I mean, this is I always forget whether this is called a radical ideal or a non-radical ideal, but it's something like that, right? It's I mean, this is right. This is the kind of thing where you take squares of ideals. This is the kind of things that like the Studi numbers is based on, or something like that. Except here it's doing, like with a prime like 3 instead of with a
Right. Yeah. Okay.
determinant like X or something like that.
Is the field Z?
Yeah, so you're getting this.
mod-
You're getting this nilpotent thing, right?
Yeah.
What were you going to say? 3 is nilpotent in Z mod 9,
Okay,
either
yeah.
over the ordinary integers
Yeah,
or
okay.
the Gaussian integers.
So we're like doing some kind of little initial bit of the Taylor expansion of a p-adic number or something like that.
That's right. That's exactly right. That's exactly right.
Yeah. Okay.
And maybe
Okay.
that
So this is
will
like-
help to make it clear why there's this little short exact sequence where if you think about it, that does help why
Oh, I guess so.
to
Yeah.
understand why there's this multiplicative
Okay.
part and this additive part.
Yeah. Okay. Yeah. So it's like this AX plus B type.
Yes,
Yeah.
that's right. That's right.
Well,
It's something to do with that, but I still don't feel smart enough to say anything intelligent about that. That's right. And another thing, right? I mean, this is obviously let me tell you one of these. This is probably important. I was going to say obviously important, but one of the things that's probably important is that what we're kind of doing here is we're taking a norm, but then we're taking the residue of the norm, modulo some modulus.
Right.
And so if you read textbooks on the Artin reciprocity theorem, they talk about something called the norm residue symbol. So since I'm taking norm residues of norms here, and since the textbooks talk about norm residue symbols, that means maybe that, maybe the real way to understand this really, maybe we are making some connection here to the standard conventional way of doing things here. But I'm not even sure of that yet. But so like I say, since I'm just still taking guesses here, there are a lot of things that I'm not very certain of yet. So like, in what generality can we apply this rule involving the norms? Well, perhaps it depends on when we took this relative extension, which is really just kind of a push out, that this relative extension or this push out was a field again. Right? If it hadn't been a field, then maybe there's some more general rule that we'd have to think about. But in evidently in cases like this, whatever that means, where we do get an extension field, then we use this norm residue rule to get the relative splitting pattern. So it's a sort of extension. Well, it's not quite an extension because it's actually different. Even on the ordinary primes, it's different from what the old splitting pattern was, but it's a new splitting pattern that tells us how the relative what the splitting pattern is for the relative extension. And right, evidently it's supposed to give us in this example, for example, it's supposed to give us an index 6 subgroup, which concretely means a 12-element subgroup. But I'm not even sure I see why this norm procedure, why it ends up giving a subgroup of the correct index. But it did work in this one example, so maybe it's correct.
But
so this could be important stuff for me to learn.
I had another dumb question. So like, you drew these two charts.
Yes.
And
which two ones? The ordinary
sorry,
one,
the big blue ones, the main charts.
Yes, the two main charts, yes.
And so
that's the ordinary one and the Gaussian one. Okay, yes, go ahead.
So like, each chart shows a bunch of fields.
Yes.
Well, you can think of it as showing a bunch of fields.
Yes.
And is it true that each of the fields in the second chart
Yes.
is just the field in the first chart, the corresponding field in the first chart, but with I thrown in?
No, that's only true towards the left.
Yeah, I thought not, because I thought it was, and then at some point you said something that, let's see, like, where did, you said something.
As soon as we start, right? I mean, so we're kind of doing an analogous thing for the Gaussian prime 2 plus 3i, as we did for the ordinary prime 7. So as soon as the 7 comes in, is where we stop having this exact, is where this. But before you bring in the 7, so that would be this, these 4 on the left of the Galois correspondence. That's the part that is just pushed out to the Gaussian field, or the Gaussian.
Could you just take that top chart and push it out to the Gaussian field?
Yes, and that would probably also work, because 7 didn't split over the Gaussian integers. So yes, you'd also get one for 7. And the only reason I didn't use that one, because I thought I thought it'd be too boring, because you'd just be reusing the prime 7. I wanted to see a real Gaussian prime, like 2 plus 3i.
I see.
In a way,
I sort of like
it would be interesting even for the Gaussian, even for 7 as a Gaussian prime, as a degenerate Gaussian prime. It would still be interesting, I think, because it wouldn't be a completely trivial. You wouldn't just copy things down. You would have to, start thinking about the Gaussian integers mod 7, which would be this 49-element nilpotent ring, and then it would have this 42-element general linear group, and so you'd have the same 18-element template for the subgroups involved in the Galois correspondence, but it would be in the Gaussian case, for Gaussian 7, it would be different from ordinary 7 in some ways.
So what about it would be different?
The
The fields would not, the fields would just all be the push outs, right? Of the original fields and the Gaussians, right?
right, but I think, like I say, you'd have
But
you have this 42 element general linear group GL1, comma GL1, comma Gaussian integers modulo 7. That would be a 42 element thing. And then you have to then you'd have to mod out by a 14 element subgroup in order to get this 3 element thing, I think. So let's see, is that right? 40, yeah, right. Why is this so confusing? Why? I'm sorry. I'm just getting something confusing here. 42 is a lot bigger than 12. Oh, okay. So then, okay, yeah, the norm of 7 actually is a lot bigger than the norm of 2 plus 3i. So yes, right. It makes sense that this 42, right? The norm of the Gaussian integer 7 is a lot bigger than the norm of the Gaussian integer 2 plus 3i. So, okay, I was just getting confused about that because it was confusing to me. But so, right, I mean, right, you really would have to take this 42 element general linear group and you would have to have this 14 element subgroup for its co-kernel to be a 3 element quotient group. And that 14 element subgroup should be given by applying the norm residue rule. Applying the norm rule to the old one. So, right, it would be these, it sounds like I'm claiming that there are these 14 classes that would, come, that their norms would be congruent to 1. No, would be congruent to 1 or 6 modulo 7. Is that right?
I don't know. I'm getting lost. But yeah, anyway, so you sounded like
I'm explaining it badly, but it's actually
uh-huh.
it's actually follow your nose type stuff.
Yeah, I mean, when you when you switched to this new thing, what was it? 2 plus 3i?
Yes. Yes.
Yeah,
I'm
saying
saying
why you did it because it's like more interesting. But to me, what's sort of like would be very pleasant is to think that like there's something less interesting going on where you do this whole first chart involving the rationals, and then they're like copies of that same post set, sitting around all over the place.
There are,
one of which you could obtain by working over the Gaussians, but they're obviously, if that works, then they're like going to be loads of them,
right?
Sitting around in this huge post set of all extensions of the rational.
Yes, but basically what I was trying to say is that if you do the ordinary integers mod 7 and then you do the Gaussian integers mod 7, those are 2 very different quotient groups. And that means that, that means that some things are different. Even if you use the same ordinary prime 7, some things are different over the Gaussian integers. Gaussian integers mod 7 is a very different ring from ordinary integers mod 7.
Yeah.
So I was trying to say that, but I said it in
a
complicated way.
Well, you just went into a lot of detail.
Yeah. So yes, but I mean, you're definitely right that this same pattern is going to appear all over the place when you take any base field, any number field as base, and then deal with some abelian cubic extensions of it.
Mhm.
And, you know, and then in order to understand that abelian cubic extension, you will be using the relative Eisenstein thing as a helper, and that will give you this whole diagram here, basically. Well, I mean, look, again, let's sort of remind ourselves of why we actually have all 12 fields in this little fragment of the Galois correspondent. And if you recall, my excuse last time was that I sort of have trouble distinguishing these three extensions from each other, and also correspondingly these three extensions from each other. Or now that I realize it, it's actually these two, this one here and this one here, and this one here and this one here. Their splitting patterns are very similar, whereas the one in the middle, that's the one that's actually doesn't even involve any congruence modulus 3. It's only congruence. It's only the splitting pattern only depends on the modulus 7. So that one in the middle actually, for some reason that I don't understand yet, sticks out like a bit of a sore thumb.
Can you remind me what that field is? Or maybe I forget.
Well, so each one of these, let's see. So each one of these three is gotten by taking the cube root of a relative Eisenstein integer. And which relative Eisenstein integer is it? Well, so you take the prime that you're interested in, which is 7 in this case, and you factor 7 you factor 7 over the Eisenstein integers, and it factors as a pair of Eisenstein primes. But then you reassemble those prime factors in a funny way so that it becomes this weak fixed point for the Galois descent. And you know, that's how we understand these Z mod 3 torsors, using this Galois descent. That's one of the ways that we think about this, using this Galois descent idea of how Z mod 3 torsors. And the Galois descent idea comes from thinking about, you know, the Tanakian viewpoint about the representations of Z mod 3. So, you know, all these viewpoints that are meshing together. And so, you know, and eventually when I'm going to put this together, this is going to be, you know, the Artin correspondence or the Artin reciprocity theorem. But you know, since my understanding of it is not perfect yet, I'm a little bit vague on the fact that, you know, my procedure says when you're trying to get this weak fixed point for, or if you prefer, call it a strong fixed point for Galois descent purposes, the procedure says to start with this prime 7, this ordinary prime 7, and factor it over the Eisenstein integers. But that's a little bit ambiguous because, right, prime factorization is always a little bit ambiguous up to units in the ring of the algebraic integers. So that ambiguity is responsible for this threefold ambiguity in which, right? And again, this is analogous to the fact that, you know, the quadratic extension for square root of 5 is different from the quadratic extension for the square root of -5. You know, because those, you know, the square root, the thing you're taking a square root of in that example is differing by a unit in the ordinary integers. And here we're, you know, so here we're right here we're differing by a unit in the Eisenstein integers, or in the relative Eisenstein integers. And so that's giving me this ambiguity. So you see what I'm saying? These are 3 different cube roots, but it's the cube roots of 3 different things, which are very similar to each other. They only differ by multiplying by a primitive cube root of unity.
But what are they the cube root of? Sorry, I'm completely blanking out. I mean, apart from that ambiguity,
Yes,
if you're like a bad college student, you just write a cube root sign and you don't remember that there's
sure, sure.
what's the simplest way to say what it is?
Well,
It has to do with
I mean, I'm saying
7.
7 is equal to, let me see if I can remember how this works. Is it like
Oh, okay.
1 plus 3 times 1 to the 1? This is how it factorizes over.
Okay, I guess we did this before.
Yeah.
Okay.
Plus 3 times 1 to the 2. I'm hoping that's the correct. You could probably check quicker than I can that that's the correct
Yeah.
factorization of 7 over the Eisenstein integers. But this is not a weak fixed point of Eisenstein conjugation, or it's actually this way. It's in some sense, in some appropriate sense, it's a weak fixed point of Eisenstein conjugation. It's not in the eigenspace where the eigenvector is. It's not in the eigenspace where the eigenvalue is 1. It's in the eigenspace where the eigenvalue is -1 for some reason. I think. Is that right? I think that's right. And so it ends up being, you just put a factor of 2, you put an exponent of 2 on one, and this ends up being, in this eigenspace of Eisenstein conjugation acting on this abstract vector space over the 3-element field.
So now it's not 7 anymore, by the way, right?
That's not 7 anymore, right? That's this. So
Yeah.
So when you take a cube root of this, I sometimes call this, I doubt that anybody else in the world does it, I call this a twisted root of 7. Taking a cube root of this is what I'm calling a twisted root of 7. The reason I'm calling it a twisted root of 7 is because I'm sort of planning to organize all the twisted roots of 7 into a certain useful extension field, but I haven't really gotten to that point yet. But yeah, see, as you say, it's dangerous, right? That's not equal to that. But
Okay, yeah, I sort of get it.
and yeah, so it's going to be the same way. Let's just imitate that now down in the Gaussian case. Okay, so we're going to have going to have 2 plus 3i is going to factor over the Eisenstein integers, or it's a Gaussian integer, so it factors over the relative Eisenstein integers. So it's factoring over the 12th atomic field, and it's equal to something times something. But you're going to then make it not equal anymore by putting that in, and then you're going to take the cube root of that, and that'll be a twisted root of 2 plus 3i, and that will generate these 3 things here. And yeah, and there's a slight ambiguity where there'll be, it's a little bit tricky for me to tell these 3 apart, because it would involve, these slight ambiguities caused by the fact that the factorization is only unique up to these, primitive cube roots of unity, or primitive 6th roots of unity, or something like that. Or something like that. So that's why I'm lumping these together. And then furthermore, this was the part that I, described as my laziness last time, that since I have so much trouble telling this little triplet of extensions, telling them apart from each other, when I'm doing calculations to check whether this is working, what I actually do is I use these things over here. This one and this one. And I do a lot of my empirical tests over here, because it's, right, these are the things that have all of those cube roots in them, all 3 of these cube roots. So I find it useful for doing calculations or something like that. So it just ends up being nice that, you know, I've been drawing this little fragment of the Galois correspondence, which includes these little extension fields over here, but it's nice that I actually found a use for those extension fields, that they're actually useful calculations that I can check by working with these extension fields over here.
Mhm.
So that's how this is supposed to work. Now, again, I'm teaching myself by examples here. And there are still all sorts of ways in which the examples that I'm doing here are not general enough. Like, for example, the Gaussian integers doesn't exhibit any non-principal ideas.
Right.
And so I want to do more examples, or, you know, I also want to understand the proofs of why this whole thing is going to work in, you know, for completely arbitrary number fields, for, you know, understanding Z mod 3 torsors, or understanding abelian cubic extensions of any number field. I want to understand that, you know, by abstract proofs, but I also just want to understand it by these kind of concrete pictures that I can draw in examples. And so I still have more examples to try where I'll be using, you know, some nice, simple, imaginary quadratic number rings where there's non-unique factorization and non-principal ideals and stuff like that. And so well, so like I say, I'm doing empirical tests to check this. I still need to do a lot more empirical tests, but all the empirical tests I've tried so far, they seem to be working. And I just need to try more examples, and I have to try to assemble all this concrete understanding of examples into more of an abstract understanding of the whole conceptual apparatus. And like I say, I'm guessing that this thing about the conventional terminology of norm residue symbol, I'm guessing that's sort of implicit in what we're already doing. But I don't know yet. I'm gonna have to really, you know, learn more about that. So I'm not sure I should really try to say much more today. It's probably, as you said, there's probably all sorts of things I'm forgetting to say. But I hope you can see what I'm trying to do here.
Yeah.
Okay. And
I wouldn't mind saying some stuff since we
sure. That sounds like a good idea. Maybe we could just stop the recording temporarily while I get my thoughts together for your part of the talk.
Sure, I'll pause it now then. Okay, so I've been thinking a bunch about separable algebras, trying to understand them from different points of view and running into them from different points of view. So you may remember I was really interested in understanding the Brouwer group.
Yes.
Of a field, but then more generally of a commutative ring.
Yes.
And then
Still basically called the same thing. You still call that a Brouwer thing or something?
Yeah, the people.
Okay.
Yeah, so I think Grothendieck started talking about Brouwer groups of commutative rings, and then he started talking about Brouwer groups of schemes. And so the thing there was basically if you've got a situation where you have some kinds of algebras, which could be like monoids in any symmetric monoidal category, so some very general concept of algebra, then you can set up the idea of Morita equivalence of these monoids by saying that they're Morita equivalent if they have equivalent categories of actions, right? But it turns out that it's also the same as saying that there's like a bimodule,
Yes.
an invertible bimodule going between them.
Yes.
So I was very interested in that.
I like that better in a lot of ways. I think.
Yeah, I like that better.
I have to think about it. I have to think about it. But go ahead. Yeah.
Yeah. So both points of view are nice, and yeah, I would prefer to just talk about the bimodules, but there are a lot of things where it's, at least at first, it seems like the equivalent, the categories of representations or categories of actions give you a way to understand things. So I was very interested in that. But you may or may not, I forget how much I've told you about this and also how much you know about it, but so one of these so to get the Brouwer group, you look at the invertible Morita equivalence, sorry, the Morita equivalence classes of invertible monoids. So monoids that have a tensor inverse.
Yes.
So
again, that's the Brouwer thing?
So the Brouwer group in the sort of super general way is you look at, well, yeah, not the most general way, but the super general way is you look at monoids, bimodules, and bimodule homomorphisms. And that's a monoidal bicategory.
Say that once again. Say what? Monoids?
Yeah, I should have used my
monoids, bimodules,
and bimodule homomorphisms.
Okay.
And I mean monoids in a symmetric monoidal category. So to get a lot of generality.
Right.
So when you have that monoidal bicategory, which is actually a symmetric monoidal bicategory, by the way, but when you have that,
let me orient myself here. Let me see. What did you call it? You called it a monoidal bicategory?
Yeah, because you can tensor these monoids with each other and get new monoids.
Can I think about that? Let me think what you're saying.
I mean, I'm assuming I'm assuming that our symmetric monoidal category that we're working in is very nice, that it has like all the co-limits you might need to do this tensoring of two commutative monoids.
Oh, okay. Wait, but
so I'm not stating, I could state all the hypotheses if you want.
Well, it's just that you say the one that I'm agonizing over a little bit is whether this is a bicategory. The bicategory that we're going to make into a monoidal bicategory, is it a bicategory of just plain monoids or of commutative monoids, or perhaps even braided monoids or something like that?
I want it to be of plain monoids.
Plain monoid, then I'm not, am I confused? I'm not sure I'm seeing that being monoidal, because, you know, when I try to make the associativity of the tensor product of the monoids, I'm imagining, I could be wrong, but I'm imagining that I'm secretly using the braiding, you know, internal to the monoid,
no, you're using the braiding in the symmetric monoidal category where all this is occurring.
Yeah. Okay, maybe I made a level up. Let me think. Monoids. Maybe I made a level slip. Let me think. Why is this confusing me?
Yeah, the category. Yeah, I think you made a level slip. I could give you an example if that would like help line up your
maybe
goals. Let me give an example. For other people will need it anyway. So like the symmetric monoidal category we're working in could be like vector spaces over some field. So then the monoids are algebras, and you can tensor algebras. And that's a symmetric. And that tensor product of algebras is a symmetric monoidal thing.
Well, that's a funny level set for me to make. Then let me think about that. I mean, I won't worry about it too much. But let me see if I can orient myself better here. No, I don't know if I can. By the way, so you can have this monoidal bicategory. Was the next thing you would say was to take the core of this monoidal bicategory or something like that?
Yeah, I was just sort of reminding you of why
some part of the core, some level of the core, or something like that.
Yeah, so I was interested in like the invertible objects in this monoidal category. So those would be called the Azumaya algebras. Horribly technical sounding term. So those would be the monoids that have a tensor, another monoid, such that when you tensor them, that's Morita equivalent to the trivial monoid. So like in the example I was giving, like the quaternions, tensor the quaternions are is Morita equivalent to the real numbers, say we're doing the real vector spaces.
Yeah, okay. All right. I'll have the part that I worry about. I'll have to. I didn't completely resolve it in my mind, but I'll just have to pretend to understand for the moment while you go ahead. Okay, so
Okay.
let's think again. One out of bicategory out of this.
Yeah.
And then I like this idea of taking the core, but then we have to kind of try to get straight which level of the core is going to be the Brauer group or something like that. It's going to be like
so the
pi 0 or pi 1 or pi 2.
the bottom level, whatever you want to call it, meaning the invertible objects form a equivalence classes of those form a group, which is an abelian group because we're in a symmetric monoidal bicategory to begin with. So that's called the
So this is
Brauer
going to be a
group.
3 type. This is going to be, the core is going to be a 3 type.
Yep.
And we're taking then take core and pi 0 of that core.
I guess then you call it a 2
Called,
type. Wait, anyway. Yeah. Yeah.
I thought it would be a
Well, we got a pi 0, a pi 1, and a pi 2. If you start counting from that number, isn't that called a 2 type then?
let me
Oh
think.
yeah, it's annoying.
Let me think. This could be connected to my other level slip. Let's see.
A 2 type has 3 different homotopy groups. If it's not necessarily connected. Just like a 2 category has 3 kinds of things. Objects.
I'm getting very disoriented about various level slips here, but let me just try to.
This is taking too long.
What time is it? Okay.
This is supposed to be the part that was supposed to like reassure you.
Sure. Well, okay. I'll just have to.
I think you actually
take it, but let me just write down quickly such a thing here. It's called Brauer group, and its elements are basically the Azumaya algebras or something like that.
Yep.
Okay. Yeah, I'm not completely oriented to the situation, but I could straighten it out if I go home and think about it.
So there's something that I've been trying to understand these, and when we're dealing with a sort of classic situation, when our symmetric monoidal category is the category of vector spaces, or even modules of a commutative ring. There are different descriptions of Azumaya algebras that are sort of more
Yes.
checkable in various ways.
Yes. Yes.
And one way that people often say is that they are Azumaya algebras are separable algebras, which are central. So whose center is just see here, R is the ground commutative ring. And I've been trying to understand a good proof of that for quite a while, and I know some proofs, but they're all too complicated, and I think I'm not done figuring that out.
Yeah.
But nonetheless, I have other things to talk about. So you see, there are these separate central.
I mean, you can try and treat the commutative case as a toy stepping stone or whatever on the way towards this other thing, right?
Yeah, so I got interested in the commutative separable algebras.
Yeah, which you can think of as simpler.
And yeah, that's right.
Easier.
Yeah, right. And so I got pulled into that, and maybe you know more about those or something, but
not abstractly.
So just to remind everybody, there's different definitions of a separable algebra. One of them is that it's projective as A is separable if it's projective as an A tensor A-op module, which is, I wish I understood that. I mean, it sounds like a good thing to think about, but I wish I understood it more deeply. But I know, starting from that definition, you can quickly get a hold of this other definition that's sort of great for people like TQFTs, which is that given that you can find a co-multiplication for your algebra, which is not necessarily co-associative, so it's not, but it obeys these Frobenius laws, and also this special law that if you co-multiply and then multiply, you get the identity.
Can I ask just an obvious question about this?
Sure.
Well, so that phrase "can be given" raises a structure versus property issue, and I'm just curious if you know any answers about that.
So it turns out that so it is very interesting. So if you want to make a good category of, so that matters a lot if you're trying to understand the category of separable algebras, whether you think of this co-multiplication as a structure or a property, and it really makes a big difference. It's not. And so it turns out that if you impose it as a structure, then the only morphisms of separable algebras that preserve both the algebra structure and this extra co-multiplication are isomorphisms. And that's because it's similar to how the only morphisms between Frobenius algebras are isomorphisms. So that's maybe good for some things, but it's really bad for some other things. And so it turns out that it's also very useful to just think of it as a property, that it can be given this, and not as a structure. And then you get more morphisms between separable algebras. And it turns out that that's actually really important in what I'm going to talk about.
All right. I'm still, only halfway following things in general here, but it's all okay for now. Go ahead.
Yeah, I mean, well, there's obviously, to really explain things, I'd have to say a lot more, and I'd also, in some cases, have to understand it a lot.
Sure.
So I decided to move away for a little while from the central Azumaya algebras to the commutative separable. Sorry, move away from the central separable algebras, which are Azumaya algebras, to the commutative ones. And then I ran into this thing that people call the fundamental theorem of Grothendieck-Galois theory, that you may know much better than me.
Maybe not. Go ahead.
But which I still want to tell you about.
Okay.
So like over a field, the commutative separable algebras are understandable. And they're just finite, I should probably say finite products, but finite products of field extensions of your field that are separable and also of finite degree. There's this sort of irritating stuff about, there's this concept of a separable extension of a field and a concept of a separable algebra. And they're defined originally rather differently, but there's like an excuse for them to be both sharing the same word. And I guess this is basically the reason. So part of what's going on is that a separable extension of a field, if it's finite degree, is also a separable algebra over the field.
Okay, and sorry, I'm not doing a great job of completely following it as you're talking, but it sounded like you were suggesting that this is some partially consistent extension of the meaning of separable.
Right. Yeah.
I mean,
Yeah, so
and that helps to explain where the
that's probably
separable came from.
That's
Perhaps.
probably where I don't know. I think that's where it came from. Yeah.
Okay.
Yeah. So basically, as long as you're working with like field extensions of finite degree or whatever you call it, then the two meanings of the word separable completely coincide.
Okay. Okay.
In the sense that, of course, not every separable algebra will be a field, but every field extension that's separable in the field, in the language of field extensions, will also be separable as an algebra too, and vice. And so,
okay.
Yeah. So then there's like another thing that people tell me, which I don't fully understand, but which I really like, which is like a more geometrical way of thinking about separable field extensions, at least, so that you can, if you have a field extension of another field, you can think of it as something sort of like a covering space. I mean, you can think of the schemes, of the affine schemes of them, and they're pointing in the opposite direction. And so a field extension is separable if this map has a nice geometrical property, which is that it doesn't map any non-zero tangent vector. So you can think of E as a kind of space over B, and you can ask, are there any non-zero tangent vectors? Well, tangent vectors on E will get mapped down to tangent vectors on the base.
Yeah, I mean, it sounds like the kind of thing that might help you to think of something as being like a covering or something like that.
Right. Yeah. So it's sort of like there's no
local isomorphism or something like that.
Right. So there are no vertical tangent vectors. So it's sort of flatly.
I'm not saying this is exactly what you would want for such a thing, but it sounds plausible that it might be. So I can imagine people using this as something like this as a condition when they're
so
a topology or something like that.
Yeah. So when I was talking to him about this a long time ago, on the N category Cafe Mignon, I said like, oh, so separable just means it's like a cover. And he said, no, it's not quite like a cover, because you could have, well, especially like if you consider the case where you aren't dealing with fields, you could have a separable algebra over another algebra, and it could have like, it wouldn't necessarily, it could, what am I saying? There could be like more sheets. This isn't, it's sort of worse. It's not necessarily a local homeomorphism, the covering map, but
are you talking about?
So then you need this other word of it, huh?
There are some notions of locally nice, local isomorphism versus, I mean, there are some cases where you work over a point of the base space. And there are other cases where you work over a point of the total space and you see, how nice the map is, or how nice the inverse images are versus how nice the little local is. That's not what you're talking about?
Well, apparently these separable things.
Yeah.
I got the feeling from what Min Young Kim told me is that these separable things, they don't need to necessarily be Étale maps. So they don't, even in the weaker of the two sentences you mentioned, they may be sort of defective.
Okay.
I don't understand that,
but I was more talking about in the other direction, that Étale may imply.
I got the feeling that so I think that Étale
under in certain circumstances or something like that. I don't know.
I'm pretty sure I'm pretty sure that that's true pretty generally.
Okay.
So one project I want to do is to understand this thing, and it should be fairly easy because there's one way to say it, which is that you can define a kind of algebra of, you can define a space of derivations of your larger field.
Yeah.
Thought of as an algebra over your smaller field, right?
Yeah.
You can talk about derivations of an algebra.
Yeah.
And so it's talking about derivations of the big field, thought of as an algebra over the smaller field. Those are like vector fields.
Yes.
On the total space that map down to the zero vector field on the base space, because your things that are living in the smaller field, they're derivatives.
Yeah, so I mean, they're like infinitesimal bundle orthomorphisms or something like that.
Yeah. So apparently separable extension of the field is equivalent to those, all those derivations are zero, which is just what I'm saying here in a more geometrical language. But that should be, but that should be pretty easy to check, because it's pretty easy to play around with the concept of derivation of an algebra, and it should be related to some of these other characterizations of separable that are. So I haven't done that yet, but anyway, so this is sort of interesting. So like there's this boring special case, but still not completely boring, which is when start out with a field that's separably closed. So it has no finite dimensional separable extensions except itself. And that means it's its own, that implies it's its own separable closure. That's a thing that people talk about. So that means that so then it turns out that all the commutative separable algebras over that field are just finite products of copies of that. So that's sort of like saying that, like in that case, you got a point that's so nice that the only kinds of covery things of this type that we're talking about are just like finite collections of that point.
Yes.
And so in that case, which is sort of the boring case, because the Galois theory has sort of evaporated because your field is its own separable closure. So then you get this easy result, which is that if a field is separably closed, so you take the category of commutative separable algebras over it, and then you take its opposite to go over to the geometrical outlook, and that's equivalent to the category of finite sets.
Yes.
And here, by the way, see, this is where we needed to treat the Frobenius as a property rather than a structure, because we wouldn't have any non-invertible maps if you imposed that this co-multiplication was part of the structure that needed to be preserved. So then you would just get the groupoid of finite sets, I guess, which is nice in some ways, but anyway. people like.
Yeah, I mean, we usually, when I talk about structure versus property, I'm usually just talking about groupoids anyway. So I'll think about all this anyway. But okay, go ahead.
Yeah. So then there's this generalization when your field wasn't separably closed. So then it will have a bunch of different separable extensions, finite dimensional separable extensions. So the way I think of that, I try to imagine it is like they're different kind of K corresponds to some kind of pointy thing. And then there could be like these covers that could have points of different kinds, one for each kind of separable extension. So I mean, the theorem is, I guess, that every commutative separable algebra over your field will be a finite product of separable field extensions.
Yes.
Finite dimensional separable field extensions. So it's sort of like a colored version of what we had before, where these points sitting over your point can come in different kinds. And so then I guess Grothendieck proved this famous thing. So you can do the same thing we did before, take the category of commutative separable algebras over our field, and take its opposite and see what we get. So now it's going to be fancier than the category of finite sets.
Yeah.
But it turns out it's the category. So it's probably like a Boolean topos. Yeah, it's a Boolean topos. But they say it's a topos of continuous actions.
Yes.
On finite sets of the absolute Galois group of the field.
Yes.
So here we're using this trickery that the absolute Galois group is this profinite.
Yes.
In giving it a topology, and then looking at continuous actions of it to make the only, I guess I don't know what to make things I don't know how to put it, to make it be that like the only the finite quotient groups of that big Galois group actually sort of manifest themselves. All of these continuous actions factor through a finite quotient of the absolute Galois group.
Yes. Yes.
Sort of keeping things finitistic.
Yes. Yes.
So that's really nice. I mean, I should have learned this much sooner, I guess. I mean, I don't know the proof, but it just seems very believable to me now. So I like it a lot.
Sorry, did you say that you do know the proof of it? And is that what you said?
No, I don't know the proof of it. I
Okay.
mean, but I can almost imagine that I could.
Okay.
I think I like almost get I think I almost understand.
Yeah. Yeah.
Because it's sort of like combining the usual Galois theory for fields with this sort of slight generalization where we look at these commutative separable algebras that are just finite products of
Yes.
field extensions. So you have extra morphisms between those kind of commutative separable algebras that can, besides the usual Galois theory, which is just like purely symmetries of one particular field extension.
Yeah.
So that's fun. And then but I was really interested in like understanding all this type of stuff, where, remember, I started out saying like we're working with commutative monoids in a symmetric monoidal category and trying to do Brouwer groups and separable algebras and stuff like that in there. So in other words, instead of just working with vector spaces over this field K, it would be fun if you could copy this stuff for other symmetric monoidal categories.
Yes.
And so you can define, because there's this sort of string diagram way of describing what a separable algebra is.
Yes.
It means you can talk about a separable monoid in any symmetric
Yes.
monoidal category, and you can talk about a commutative separable monoid.
Yes.
So you can copy this stuff.
Yes.
And so it turns out that somebody already did. I was wanting to do it, but it turns out someone
Well, I
did.
was gonna, I thought it might be that guy from Brooklyn.
What guy from Brooklyn? Sorry.
He has a Brooklyn accent, doesn't he? But
Wow,
I don't know. Who is it?
I don't know.
Oh, okay.
Messing? No,
Is that the guy?
no, he may be from Green works with this guy Messing, but I don't know if Messing actually has a Brooklyn accent. I know he's from New York. Well, I don't think it is. I don't think
okay.
it's from Brooklyn,
Okay.
because the guy that I'm thinking about is Aurelio Carboni, who I think is
Okay.
like
Oh, okay. Okay.
really real Italian.
Okay.
So like Carboni and Walters did a bunch of stuff on
Yes.
on Frobenius algebras, which they tended to call like separable algebras or something. Separable Frobenius monoids and stuff. So this is a paper which has this really funny title, Matrices, Relations, and Group Representations, which is funny because if you like went into it thinking that
Yes.
like, oh good, well at least I know what those three things are, then you'd be like sorely
Right.
surprised. It sounds like something that like Levere would do. Like that,
Right. Right. Right.
I'm just humbly talking about these things. But yeah, so his theorem is that is to like take a sufficiently nice symmetric monoidal category and then look at the opposite of the category of separable commutative monoids in it and
Yes.
try to generalize this Grothendieck-Galois theorem.
Yes. Yes.
So he worked with a compact closed additive category with co-equalizers. So that would be like, of course, that would like include the case of finite dimensional vector spaces over a field, which is sort of what we were talking about before, although I didn't say
Yes.
finite dimensional right on top, but here he's like putting that in right on top, that everything has a dual.
Yes.
And we need the co-equalizers so that we can do things like tensor to
Yes.
tensor to actions of a monoid and get another action of a monoid, stuff like that. But it's pretty an additive, so that's forces us into the linear algebra land a little bit.
Yeah.
But anyway, with those pretty weak assumptions, then he gets something which I do not understand, which is that you get, oh, sorry, I should have removed this word essentially small here, actually. You get something people call Boolean pretopos. And
Yes.
this goes beyond my tolerance for topos theory a little bit, although I did look up the definition of a Boolean pretopos. But
Yeah, it's not that bad, but go ahead. Yeah.
yeah, so anyway, so it's like almost a Boolean topos in some ways. But I mean,
you can probably get a Boolean topos from it. But anyway, go ahead. Yeah.
Yeah, I mean, the name pretopos sure hints you'll get there should be some way to improve it to a topos. And I was asking people here in this blog article, like, do they know anything about that? No one's said anything about this post yet. But so yeah, so Todd Trimble said that he was like surprised that you could get a Boolean pretopos from such weak assumptions. I guess he's thought about separable things a bunch. But anyway, I sort of like this stuff and I want to learn more about this stuff. And I
sure.
think that this commutative stuff, which will help me actually, I think it will help me actually deal with what I was sort of originally interested in, which is these non-commutative things, but it really also intrigues me even all the more about the relations between the non-commutative stuff and the commutative stuff. Like, for example, the Azumaya algebras, which are like only interesting if they're non-commutative, they give you this Brouwer group. They're elements of, they give elements of the Brouwer group. And there's this very nice way to think about the Brouwer group as a second cohomology group of the Galois group. Say like you're working over a field.
Yes.
And
Yes.
and so you can see even there that there's like a connection between the Galois group and this Brouwer group. But here in this commutative world, sort of all you're seeing is the actions of the Galois group. So you're seeing the Galois group. But the really cool thing the part where it gets really cool is that the kind of cohomology group, second cohomology of the Galois group, which is describing the Azumaya algebras, if you like unravel what the cohomology is doing, it's actually describing gerbs over, if you think of the Galois group as like a fundamental group of some space.
Yes.
Okay, like what kind of thing would be described by the second cohomology in the multiplicative group?
Yes.
Sorry, it's second cohomology with coefficients in the multiplicative group of your field. So that's what's classifying gerbs. And you can think of those. But it may be a better way to think about it actually is that you can think of that particular cohomology group as classifying things that are locally look like matrix algebras. So they think of them as like vector bundles, which are like algebra bundles, where the fibers are matrix algebras, but they're not trivial. So that you can like glue them together with an outer automorphism of your matrix algebra. So that's how you should sort of think of these Azumaya algebras, is they're like things that are like locally just matrix algebras, but globally have this twisting. And that's why when you take an Azumaya algebra defined over some field, and then you like tensor with the algebraic closure of the field or the separable closure of the field,
yes,
you get an Azumaya algebra over that closure. But the Azumaya algebra over the closure is just a matrix algebra. There's no excitingness anymore. So what you've done is you've taken this sort of twisted algebra bundle over some space and you've lifted it up to the universal cover, and then it becomes an untwisted algebra.
Yes,
bundle.
yes.
So anyway, this stuff is really exciting to me because for one thing, it's some kind of interplay between commutative algebra and non-commutative algebra that I'm curious about.
Yes. There's a lot of stuff here I'll think about, but I think I'm getting halfway getting the point.
Yeah, that was it. That was the
Okay.
spiel.
Okay.
Do you have anything you want to say about it now, or do you want to?
Anything about what you just said?
Yeah.
I don't think so. I just need to think about it, I think.
Okay, I'm expecting I'm expecting that sometime you'll tell me something about it that will be
it just
surprising.
it connects with a lot of things, but I don't think I can say about it yet.
I'll just say one other thing then, which sort of like rounds off the picture.
Yes.
So remember how he took the core of this symmetric monoidal bicategory, and then he said, oh, we're going to focus on the pi zero of it, which is the Brouwer group.
Yes.
Like of your field, if we were working in the field case.
Yes.
But then the one up above, the next one up is called the Picard group.
Yes.
So it's like the group of invertible modules, and that's actually not not interesting when you're thinking about a field, but
Right.
but for like a commutative ring.
Right.
And the interesting thing, as you know, is that Picard group, it's when we take the geometrical point of view, that's the first. So we think of our commutative ring as a kind of space. The Picard group is the first cohomology group of that space with coefficients in the multiplicative group.
Yes.
So the Picard group is like classifying line bundles, which is something that, of course, we've talked about a huge amount in these conversations.
Sure.
Yeah. So there's some funny, interesting kind of upside downness going on here, that when you're going up from pi 0 to pi 1, it's the same as going from the second cohomology group to the first cohomology group.
Yeah.
I don't understand that upside downness.
I have to think about it. I get confused by things like that, but it's probably not that surprising. But I'll think about it.
Yeah. So anyway, so that's like also part of this nice geometrical picture, and then the top part of this homotopy 2 type would be the group of units of your so somehow like invertible functions on a space are like units, then line bundles on the space are like the categorified invertible objects, and we talk about that tons. And then like gerbs are the invertible things at the next higher categorical level. And you might think like, well, if you're gonna do that, you might as well just keep on going, you know. They're like 2 gerbs and so on. But for some reason or other, this Brouwer Picard units group picture, it sort of fizzles out. But it does include that Derby level as part of what it's able to see, so that we're not just like bringing in gerbs just like for the hell of it, just because we feel like categorifying familiar concepts, but it's in there. And I think Grothendieck like figured this stuff out, actually. I think well, he and his compatriots, I think they like brought in gerbs partially for this reason, although I'm just like very slowly catching up to what the heck they were doing.
So
the gerb is a thing you can use to twist a matrix.
And people do talk about n gerbs all the time. And
so these days people go on and they talk about n gerbs,
but that's not really showing up here yet.
That's not showing up here yet. Yeah, so there's something about what I'm talking about that is in some way degenerate if you wanted to study n gerbs. It fizzles out at that point. But I don't mind that. I don't mind that it's a bit degenerate. I already think this is like such a big, nice thing. There's lots for me to study there.
Okay.
Yeah, so that's the spiel.
Okay. Anything else today?
Nope.
Okay.
Nope.
So thanks a lot.
Okay.
I'll see you.
Yep. See ya.
Bye.
Yep.